being the ultimate speaker, I'm also a little bit different type of thing than usual here. And from my background, it's obvious I'm a software guy. I'm bringing in a software perspective here to what is, by and large, a fairly hardware-centric audience from what I've sort of noticed in the past. And sort of somewhat unusually, I'm bringing in a little bit of a historical perspective as well. Generally, when you see a paper entitled, or a presentation entitled Vectors Are History 30 Years Later, you can tell there's some time period going on. So summarizing up front, there's sort of three things that I'm going to look at conveying in the presentation. The three big level things, and then some amount of detail or whatever around it. Number one, vector units have been way underappreciated or way underestimated in terms of their value, partially from a historical wrap. Second one, a large part of things depend on the type of problem you're running, and vectors really are very good for a large number of problems. In particular, the one that's probably the one here, in terms of vectors, they're, when you have very predictable, very regular type of computations, vectors are probably the best thing in the world for doing them. Third one is that, AI is one of those areas, AI machine learning is one of those areas where vectors probably play a lot bigger role than people tend to give it credit for, or can play. And part of what I'm going to be doing is sort of coming in and presenting that and sort of thoughts behind that. So starting out, motivation behind the, where we're coming here, and particularly the title Vectors Are History. If you go back into time in the early 80s, during the 80s, the supercomputer market, mini supercomputer market was growing incredibly fast. Cray was leading the supercomputer market. Lots of entries in the mini supercomputer market. Some of them are listed on the right. We got some real ancient times there. And you also can sort of see the performance that they were getting, as well as the fact that with a few exceptions, some of them were getting incredibly poor percentages of peak performance. Some actually did fairly well. So there is clearly some technology or something around in that. But big picture, if you looked at this in the 80s and you made the statement, vectors are history, no one would have believed. It was a radical statement, I guess is the right way of putting it back in those times. So the person who did come around and make the statement was Forrest Baskett in a paper in 1989. His predictions, which will be sort of graph form shortly, is that given that the performance of superscalar machines relative to cycle times was increasing radically at that time, vector processes were staying steady. So in the mid-range, they were at a distinct disadvantage. Still exist in the high end simply because it was the only choice, the only way you could get that fast. But it was still sort of coming around. So his prediction was that vectors were history. And if you look at the results in the 90s, pretty much all the vector machines went out and went out of business. Sort of historically, that tends to be an unfair rap in some ways, because many people condemn the whole vector market around it. But the real key as to what led to it is this graph right here. If you look at the trends of the cycle times for scalar machines versus cycle times for vector machines, or the cycles per flop, the scalar machines were trending down, vector machines were flat, and as a result of that, just couldn't compete. Look at that same analysis now, and you see a very different type of picture. So you look at this graph, I realize it can be kind of hard, or looks a little bit hard to parse. But quick summary is, there's vector machines and scalar machines on there. And can you pick out which ones are which? It's actually fairly easy. These are the scalar machines here. These are the vector machines up here. It's all a flat line. Nothing is increasing anymore. So it's made for a very different type of situation. One of the reasons it is that way is that many people recognize it. And it is moving to the point when everything in one way or another is getting vector or some form of parallelism in there. So question out of that is, what makes for a successful vector machine? Forrest actually answered that back in 1989, and it's worth going over and reviewing. The difference between the machines back then that were successful and not successful were threefold. The absolute key was they had to have both a fast scalar, he calls it scalar, actually means integer unit, as well as fast floating point processing. Second key, and the key one, the critical one in terms of going forward, is there had to be some form of cache data, some form of fast access to frequently used data. And particularly it had to be vector, something in the form of vector registers. Memory to memory machines, you ended up running at the speed of memory. If you had machines with very small registers or not enough ability, you didn't get any of the reuse. And the real key, the real area where you're getting the fastest access or getting the full speed of the vector unit is when you have the vector processor running at absolutely the fastest speed by running on a vector register rather than having to wait on the memory. So third aspect of that is that you also have to have a relatively fast memory. And in fact, one of the definitions of vector machines, from people in my time, is that it has a setup to be able to load to load memory into vector registers extremely fast. Those were the three that Forrest specified in his paper. Fourth one, which is equally important, and one of the reasons why there was a big differentiation of machines is the software. In particular, you need a compiler that can parcel out the things well, among different processors, whether it's a vector processor or a parallel processor. That was the real key between the differentiation of the machines back then and now, between the ones that were the fastest and the ones the slowest. And that's why, now it's one of the key things. And, one of the key parts of this talk is that one of SiFive's key focuses is on software, on this part here. So compiler is a really key part. One of the important things of understanding there, following that, is understanding what it is, what are the type of applications, how does a compiler work? So you can know when it will do well with a vector unit or other unit and when it won't. One of the things you find, sort of universal experience among people writing programs for parallel machines and vector machines. Expectation, they come in, they write the program for parallel execution, they make the changes, they work through the syntax compilation errors, execute, they're going to expect they get performance like this. Everything's lined up, get performance, everything's speeding down freeway, and all is going fine. Reality tends to be a little different. They go through everything, they come around. When they actually come around to executing, what they get is this. What they quickly find is things almost always run slower when they come in unless they've gotten a really good compiler, really good system. And as a result, what they end up getting is the equivalent of traffic in Bangalore, where everything is bottled up trying to get to memory and trying to get results to and from memory. So the real key, and one of the arguments for vector architectures as opposed to more highly parallel architectures or more scalar architectures, is it has that regular path to memory. It does have a way where you can get execution like this. You can get things lined up going in a very predictable fashion and not everything clogging up where you have thousands of processors or thousands of threads trying to access main memory all at the same time. You hope that it lines out into this dynamically, but it doesn't always do that. And one of the advantages with vector units is that you can make it do that way. So what is the real key out of those to getting performance? On the left is a graph that shows, even back in the 80s, the data here is from a paper by Jack Dongera. It's entitled Squeezing the Most Out of a Vector Algorithm in Vector Fortran. For the machine this is running on, 200 megaflops was the peak performance, the blue line across the top. Green line for these various, really key kernels that tend to be used in numerics, but are also important for a lot of them in AI, is what you got just compiling straight through the problem, just compiling the C code or the Fortran code back then straight through. The red line is what you could get by just tweaking the thing a little bit in order to get better memory use. The real key, that is noted in the paper is that it's not so much the peak performance. It's not the number of processors that you have. The real key to getting performance on a highly parallel machine is being able to get memory data reuse, to be able to reuse the data you've used in computation, get it in there and get the fastest speed, repeated, allow the processor to operate at the fastest speed. So if you look at the graph on the right, that's basically to come around and, showing the three factors that come in, comparing scalar data and the reuse. Oops, sorry about that. Let's see if we can, the blue line is sort of scalar performance as your register size, as you do iterations across. The red line is vector. You have some initial startup, but it's going to go in increase. So there is a point when vector definitely goes over, and improves over scalar, and you get a thing. But the real key of all of that, in terms of setting the vector register size or setting the register size, is the reuse. If you set the size of the register to be 1, then you're going to get the, you have the equivalent of a scalar machine and those types of vector units. You've got lots of reuse in there. Depending on the number of registers you've got, you can reuse that number of pieces of data. When you set this register size to 2, that halves, because now you basically have registers of size 2, and in terms of the number of values, the number of variables that you can reuse, you've cut it in half. As you go farther out, you get more and more to where when you go all the way out to the end, you have no reuse whatsoever because you're going memory to memory. So what that says is the real sweet spot, the place where you get the best vector performance, is when you get some area where you get the right combination of reuse and enough there to be able to get the vector size to you get the benefit from the vector unit. So key part of it more than anything else, that all depends. That's all depends both on the application and the particular architecture. But the real key is it isn't down at 1, and it isn't up at some very large vector registers. It's application dependent, and it's architecture dependent. And one of the real strengths of the RISC-V architecture is that you can set the size of the vector registers to be whatever you want to adapt it to your application and do things around. So that's the real key, that and having software to exploit that. So a famous quote, I first heard it from Cleve Moeller, but I think it gets attributed to Seymour Cray more often. And it's always phrased a little bit differently. Sometimes it's plowing, sometimes it's crossing the prairie. But the statement is, if you were crossing the prairie, how would you like to get across? In a wagon driven by 2 sturdy oxen, or in a wagon pulled by 1,024 chickens. Usual answer to that is the 2 sturdy oxen, and I'm certainly putting things that way. But the real key is to recognize that there are times when it's both. If you compare this, look at this is equivalent to a vector unit. If you got one computation where everything's trying to pull in one direction, and you need very regular, very strong, sturdy pulling, this is absolutely the way to go. And that tends to be things like matrix multiply, AI types algorithms and stuff like that. If you're doing in something where you have another way of maybe phrasing this one using the plowing analogy, if you were trying to plow 1,024 rows in a field where they were wandering around different way, this might be the way to do it. But if you're trying to pull forward on one computation, you're going to get the equivalent of the memory bandwidth, or trying to pull everything in together, get it all focused in one direction, is taking more effort than you get to pull out of it. So the real key is that, in terms of utilizing parallelism, it's getting that balance here. And that vector units provide a lot of the balance that comes around, that you get out of the type of situation on the left. Okay, so a little bit, one slide on compilers, because that is an important part of how things work and what makes the difference between where vector units are really good and vector units are less than good. Sort of 3 types of applications that you tend to find in terms of their memory use, whatever. The absolute best ones are what I call predictable applications. The way a restructuring compiler works is it analyzes an application at compile time, tries to figure out exactly how the memory access and the computation is going to go. If it can predict that, then it goes and reschedules that or schedules that to get the best optimal execution at runtime. So matrix multiply, which is the first one, is the absolute perfect predictable application. Compiler can look at that and tell exactly what's going to be done on each step, exactly each loop iteration, exactly what's going to be compiled when. And because of that, it's able to compile and execute things very, very fast. It's very efficient. Second type is regular applications, things that do things regularly but not predictably. It's sort of a little bit of a half one there, but FFT is probably the key one of that. FFT is doing the same things over and over, but it's not predictably so because the stride and the loop bounds are changing. So compilers can do so-so on that. They do well, but not nearly as well as predictable applications. The last one is what I'd call the regular ones, and those are the ones where the 1,024 chickens come in. With that one, doing matrix multiply, but over a sparse matrix is the the thing that comes in. There's no way compiler can predict that, so you're almost better off with that one with the 1,024 chickens that come in with the predictability. Okay, just quick examples of those and how those run on the SiFive. FFT, the regular but not predictable, this is actually, this is getting the percentage of peak that it can get in. Our handwritten version does. 84%, across according to size. That's actually very good percentage. And one of the important things to realize in this, didn't put it on the slide. This is a straightforward RISC-V, standard standard architecture without any customizations in for doing the things you can do to speed things up on FD in terms of bit reversal in the addressing and stuff like that. So really is, really is outstanding numbers. And if you were to go in, the advantage of the RISC-V is you can go in and customize the instruction set to put in the bit reversal and stuff, and you want it and get really outstanding if you want to go higher. Similarly with, matrix multiply, things you can get out at this one, you can get on the vector unit, basically the peak performance out of what you're looking to get, out of what the architecture predicts, with very simple coding, very little recoding. Sort of another other kernels here that, show speed ups that you get with the vector unit. These are all the types of things you'd expect to get, on a vector machine. They're all good types of things. But, you can see overall the main, you get a 10x speed up out of it over scalar, which sort of twofold again. Number one, you can get really good speed ups with vector. Number two, this is a regular type of thing where you're not getting, with these things, with compilers, you can get this without getting the memory contention that you get in more parallel architectures or highly parallel architectures out of that. So just a little bit, like I said, I've sort of implied, the thesis is that RISC-V vector is very good for AI, something I certainly believe. In terms of looking at our portfolio and what we're, looking out and coming out the timeline in our roadmap, doing, at the moment, we have 3 series here coming out, all of which with scalable vector units, all around which focused varying, starting from sort of low end, moving up to the high end. And all that give the performance that can come around and, do the things we need in there. So summary out of all this, what I hope you've gotten out of this is that, vectors, and particularly the RISC-V vector unit, is something that can provide the right balance between memory and compute when done well. And one of the key parts of that is software, which is one of the key areas that SiFive is focusing on, providing the right software to be able to provide, to get the ease of that programming, the efficiency of those units without the complexity of the programming. Particularly the V extension that's on RISC-V and that SiFive is putting out first is is one of the best ways of providing the reuse, the ability of reuse of the vector registers, or the reuse of data, so that you're able to get the most effective performance out of the architecture. With the RISC-V architecture, you are getting getting things to compute at the power of the processor, rather than at the limited by memory speeds and having the contention and stuff there. So the real key in terms of all of this is that RISC-V is balanced on finding the right balance of hardware and software. SiFive, in particular, in its version of it, is focusing intense efforts on providing the right software to make this all programming this easy, and where you can take advantage of the peak speed that you get, peak speed available in the processor, rather than being limited by the memory speeds that you've got there. So, quick summary, quick thank you there. At that point, happy to sort of switch it over and go and take questions.
Okay, thank you very much, Randy. We'll now start a 10-minute Q&A period. Remind people, you can just go to the Q&A button at the bottom of your screen and type in a question, and we'll take as many as we can. So I see we've got some appearing right now. First question, what differentiates the VI2, 7, and 8 series? What is the timeline of availability for each?
So with respect to the timeline, Steve, I'm the compiler guy, I'm the engineering guy, probably another different thing for this rather than a post. I'm not the marketing guy. So the most accurate place to get that information is on the website and coming around. I'm not quite, quite clear on that. With respect to the, and particularly again with the details of the architecture, obviously we're increasing the speeds and stuff as we go through there. But again, the right place to get that is, to contact the marketing guys, and they'll get that to you.
Yeah, I can partly answer the question, is that the vector extensions have not been ratified yet by the RISC-V community. So obviously the final versions of the RTL, production RTL, can't come out before the ratification. And
well, they can, but it would be a very, very foolish decision on our part to do that.
Right. Yeah.
But we're not foolish people.
That's right. And from what I understand, you're up to, it's going to hit to version 0.9 pretty much any day now. And I think the timeline I've been told is that version 1.0 of the vector extensions will be submitted by end of June. And then there's a 45-day comment period. And assuming that there's no serious problems arise, the extensions will be approved. And so then by the end of August, they'll be approved. So at sometime after September 1st, you could start seeing cores coming out with the extensions.
Yeah, we certainly are, we're working hard to make sure we're not very far behind the extensions when they come out. That said, having dealt with committees before, I hope that we hit that, but there's always some kind of, something that comes around and slows the committee up one way or another. But
yeah.
Hopefully they hit September, and we plan on being ready as soon as possible after that, with officially supported RTL.
Right. Well, these extensions have been 5 years in the making, so there's quite a few cooks have had their fingers in this broth.
Yeah.
So we'll see. So let's get to some questions here from attendees. We have a question here. Which paper did you refer to in the presentation?
So if you look on the footnote page, when they put the slides out there, it actually has all in. The key paper, the one that's the title is Vectors Are History, is a paper, Vectors Are History by Forrest Baskett, who was at the time at SGI, is now at NEA, well-known researcher in the field. But it occurred in the international, it was in 1989 in the European supercomputer talk. There are a couple others that are referred to around there as well. One that gives the compilers, the one that gives the compiler efficiencies, that shows, the Ardent compiler at 40% a peak on LenPack, most of the others down, was also in an international supercomputing thing. And in terms of being able to get the speed on compiled versus hand, it was a paper by Stanley Eisenstadt and Jack Dongera that was in a journal. It's in there in around 1987, 1988. Old timers there.
Mm-hmm. Okay, another question. This is a bit long here. SiFive VI cores have vector link flexibility, but only one vector pipeline. Many ARM Neon processors have multiple pipelines issuing multiple vector computation instructions. How do you compare the efficiency figures of compiler-generated code in general for both approaches?
Well, I mean, a good compiler for either one can sort of get the best that's possible there. That really depends more on the compiler than anything. I mean, the one difference, in terms, so that said, there are some architectural differences that come out of both. One of the key parts for the RISC-V, the SiFive, is, once you've got vector register and once you're cranking up a vector operation on that, once you get past the initial overhead, you're generally operating much faster than you are with, sort of shorter vector links and whatever there. I mean, once you get it going, it's going to go fast. And if you're reusing in the vector registers data so that you don't have to go back to memory, then you're getting very good efficiency. Key difference there on something, with the shorter vector links, even though you have multiple pipelines, you're limited on how far you get the efficiency of the, what's in the particular pipeline. Your particular pipeline is efficient, but you're getting, you have to get more things flying in parallel. So long-winded answer, pulling that to a shorter one, a shorter answer. You can get good out of both. Compiler can, a good compiler can handle either one. My viewpoint, what I've observed just, from many years of experience, when you get the longer vector registers, you do much better than you do with the shorter ones, because it's hard to get enough different operations in flight to come around and be able to take advantage of those.
Yeah, also, if I'm reading something into his question, the pipeline can be any width.
I missed the last part of what you said. I'm sorry, could you repeat that?
I said I'm reading something into his question. The vector pipeline can be any width.
Yes, yes. Yeah,
So there's only
so it's
one.
definitely, I mean, compilers, I mean, I've actually worked, going my history on pipelines, on vector pipelines that have done both. You know, it's definitely, it really comes down to the application and how good the, how well the application fits the architecture.
Okay, another question. Is the LLVM compiler better suited versus GCC for vectors, and why?
I mean, more, sort of personal, LLVM was created farther down the line and with a focus more on the application area, whereas GCC evolved along with Linux and is focused very much on the, deeply embedded Linux kernel type of things. Those are two different application spaces. So just from observation, GCC and embedded is very hard. There's not a whole lot of vector code as a general rule in embedded world, and that's not where GCC is focused. So I mean, a little bit of different answer to a different question than you ask, but I'd say that LLVM's application area is much better suited for vectors, and the fact that it is a newer compiler, doesn't have as much accumulated history as GCC does, means that it's a better basis, a better place for building vector compilers. But that said, either compiler can be, compiler is and my own personal thing, if I were building a vector compiler, I would go with LLVM over GCC just because of the history and the hardness of change. But that said, either compiler can be made into a a good vectorizing compiler.
Okay, we have a question regarding VLEN, which is the parameter that sets the length of the vector register. The question is, a larger VLEN can increase throughput, but won't it also increase power consumption? Does VLEN have hardware implications? Is VLEN a software application tunable hint to the data type so the compiler knows how far away compute is from memory?
Yeah, so good question, Richard. Let me see if I can sort of fumble through that again with the caveat that I am a software guy. I learned very early on in life that I'm a software guy, not a hardware guy. It will also, I'm sure that increasing VLEN will increase power consumption. It is built into the hardware in RISC-V. It's not a software type of thing. And one of the key advantages, one of the opportunities is it opens up from a software point of view is that the software, it's possible to build software that analyzes the application and chooses the right VLEN for you in terms of things. So.
Okay, here's a question, another question about power consumption and register file size. I think we've sort of answered that. The bigger your register file, the more power will probably be consumed. I think the register file size is fixed at 32, but the length is adjustable.
Yes.
Yeah.
Yes. And you're right. It's sort of obvious thing. The bigger you get it, the more power you're going to consume. So.
Right, and also it's implementation independent, right? I mean, you can implement a register file in SRAM or in flip-flops.
Yes.
Right. Okay, another question. How much improvement if compare the RISC-V vector extensions with typical vector coprocessor? Do I need a special compiler to compile my own AI software to use the SiFive RISC-V vector implementation?
So I mean, so there's improvement in performance, there's improvement in programmability. A vector type of coprocessor or any other type of coprocessor, by and large, is pretty much guaranteed that they're going to have separate memory spaces. The ideal thing in the parallel world is that you have, ideal thing from a parallel programmer is that you have a shared memory space. Pragmatically, they always end up being distributed, or separate. And one of the big problems of using a typical coprocessor is moving the memory back and forth at exactly the right time. Getting it there when it's needed, getting it back, and optimizing, getting the data reuse that way. That's a really hard problem, really painful thing, and not things that tend to do well. one of the big advantages of the RISC-V by having the vector unit integrated in is you have a common memory space, so it's much easier to compile for. Compiler is much better able to handle automatically reusing vector registers and having a fallback on than having to move memory back and forth to a separate memory. So I mean, I think the key advantage there is more the ability to have a unified memory, and in addition to having a shorter path to memory, would be more than the other things that were pointed out there.
Okay. We had a question from someone who couldn't find this paper you referred to online, this Vectors Are History paper. I'm assuming he's assuming to a paper instead of your presentation. By the way, all the presentations at this conference will be available for download within a day or two when we get them all together and put a link up. You'll get an email with a download link. So if you're talking about the presentation that was just seen, you can download that soon. Maybe he's talking about some other paper, Vectors Are History.
Well, I'm sure he's talking about the paper that's in here, and it's one of the things that separates people like me who did their PhD dissertations in the 80s versus those who've come along in 1990 or later. In that, if it's not on the internet, it tends to be impossible for the Google generation to find or realize. So it is, it is. I doubt it's only anywhere online because it's far enough back to where it's before that Google generation. It should be available out there. Like I said, there is the presentation last page contains the reference to it. And if you want, you could tell my graphs, and some of them came actually out of the paper copy because they've got the smears and stuff of 30 years on them. You can also send me email, and I'll be glad to send you a copy if you want.
Okay. Yeah, he clarified that he is referring to Forrest's paper. And another person asked, can we also watch the recorded video later? And yes, I believe we will be posting a link to for people who watch the recording of the presentations later. So we'll have that ready soon also. We've pretty much run out of time here for questions. I want to thank all of you for attending today's live stream of the Linley Spring Processor Conference. And I want to invite everybody to attend our Fall Processor Conference, which is scheduled for October. So again, thanks to everyone. It went pretty well. And maybe I'll see you in some of the breakout rooms. Thank you.